Good morning, everybody. Yeah, this is Abdullah Al-Wirdi presenting fairtool.org, an initiative to implement the FAIR guiding principle in practice. It's an ESIP seed funding project. I will go with you through the 15 principles. I'll show you how we choose the properties and the classes to implement those FAIR principles. First, definable. F1 metadata are assigned a global, unique, and persistent identifier. We choose the property called identifier from schema, linking schema data set to property values and assigning identifier like DOI and handles and the others, and also assigning metrics like rating value for this principle. Next, we have the F2 data are described with rich metadata. We choose the property called item list elements, linking dataset and list elements, and listing all the properties that form the rich metadata, and also inserting the metric value rating for this principle. Next, we have the F3 metadata clearly and explicitly include the identifier of its data. We choose the identifier again to represent and insert the identifier of the data of that metadata. Next, we have F4. The metadata are assigned, registered or indexed in the searchable resources. We choose the schema included in data catalog, linking the data set with the data catalog, and registering all the repositories and indexes that contains this metadata and data set. Next, we move to the accessible. A1 metadata are retrievable by their identifier using standard communication protocol. We use a property called standard of from computer network ontology, linking the data set to a protocol class from computer network ontology, and registering the protocol like HTTP for this principle, and giving it a rating for that principle. Next, we have A1.1. The protocol is open, free, and universally implementable, linking and using the property of confirms to linking protocols to standard, and inserting the standard like TCP/IP, since it's open, free, and universally implementable, and giving it a value metrics and rating for that principle. Next, we have A1.2. The protocol allows for an authentication and authorization procedure. We choose the access right property from DCT, linking the protocols from ComputerNet to DCT right statement, and inserting all the statements for the authorization and authentication procedures. And if this is inserted, we will give it a value rating. And then next, we have the A2 metadata should be accessible even when the data is no longer available. We choose the schema is part of property to present this principle, and assigning all the identifier in those repositories, and giving it a value metrics for this principle. Next, we have the third interoperable FAIR group. I1 is the metadata use formal, accessible, shared, and broadly applicable language. We choose the distribution from schema, linking dataset to data download, and the only encoding format for this principle is RDF, that will allow interoperability with other metadata, and we given it a metric. Next, we have the I2 metadata uses the vocabularies that follow FAIR principles. We use a property called void vocabulary, linking the dataset to a property value, and we insert the vocabulary that follow FAIR principles. At this point, it's FAIR-O, which is this ontology, and given it a rating score. Next, we have the I3 metadata include qualified references to other metadata. We use the references from DCT to indicate the references of the other metadata and insert the property values of that metadata. And then finally, we come to the reusable R1 metadata are richly described with the plurality and accurate relevance attributes. We use a property called has quality metadata from the data quality vocabulary, linking the dataset to data quality vocabulary class called quality metadata, and we given it a value rating. And next we have the R1.1 metadata are released with a clear and accessible data usage license. We use the schema license property to represent or describe this principle, linking dataset with the DCT license document, and we inserting all the licensing documents assigned to this dataset, like community commons, and we given it a rating. And then we have the R1.2 metadata are associated with detailed provenance, and we are using DCT provenance to link the dataset with the class called provenance statements, and we are indicating all the provenance related to this dataset, and we given it a metric value. And finally, we have the R1.3 metadata meet domain relevant community standards using the property called conforms to, linking the dataset to a class called standard, and we are inserting the standards that this dataset is following, like ISO 19115, and if this is inserted, we will give it a value rating. Here we have like a procedure how to calculate the fairness score of the dataset. We are following the 5-star open data deployment scheme by Tim Bernard-Lee. He indicated the stars from 1 to 5 according to the openness of the data and publishing in the net. We categorize the 15 principles in five categories: 1 star, 2 stars, 3 stars, 4 and 5 stars. The 1 stars is the basic core. The 2 stars, the 1 star is the basic core like F2, F1, and A1. The 2 stars is the enhanced access represented by F4, A1.2, A1.2, A1.1, A1.2, R1.1. And the 3 stars representing the use of standards, and this is I1, R1.3, F3. And the 4 stars, which is the rich and the fair metadata, and represented by R1 and I2. And finally, we have the 5-star, which is the provenance and additional context, and this is represented by R1.2 and I3 and A2. If we calculated all the stars of all those 15 principles, we will get 43 stars. And if we multiply this 43 stars by constants 2.3256, we will get 100% fairness score. And if we get less than 43 stars, then the fairness score will decrease. How to get involved? You can go to the http fairtool.org and contact us with your concern or requests. You will find in the bottom of the page contact us link. Also, you can go to the GitHub page under eSIB feed under Fairtool page. Any suggestion, comments, contributions, and collaborations are welcome. Thank you. Yeah.
So we're going to have 4 projects. These were all funded ESIF lab projects that I think this batch was $8,000 or less. And so these are all projects kind of getting their report out from their initial funding. So Abdullah was funded 2 rounds ago. This kind of update, the development of the Fairtool has continued. So we'll have each person present and then have questions, and then we're going to have a little activity at the end. So do you have a question in the back?
We will have a demo session tonight.
Yeah.
And we will present this on a use case. You can see it live.
Test, hello?
Yeah, I like the 5-star ratings. Did someone else develop those? And do you have a kind of a concept of maybe in terms of I was thinking of maturity framework where level 1's like performed, level 5 would be optimized.
Yeah.
Is that congruent with what you're doing with 5 stars?
Actually, this is like a report in the Europe Commissions. They developed this 5 stars from like less maturity to provenance, which is the highest. Okay. And actually, this tool, you can rerun it and update your data sets if you have available data, and then you run the score, then your score will improve. So this is an indicator for you that you can improve it. Cool. But this is from Europe Commissions that they suggest this 5-star categories and those 5 categories.
Great, thank you.
Abdullah, thanks for the update. Every time I hear you talk about this, I think I need to talk to you about this. So okay. That's going to happen this time. Yeah. Do you have examples of applying it to? The idea is to apply. I missed maybe the first slide, so I mostly saw your sort of mappings of things. Have you applied it to repositories and?
No, I have a use case. I'm taking like a data set and I apply all these things and it's ready tonight. We'll see it.
Oh, tonight, okay.
Yeah, how those are. It has 4 tabs. Each tab, it has each principle. Each principle, you can click on it and enter the data of that principle.
And did you do that for one data set, did you say, or did you do it for?
Yeah, it's like just started. Yeah, this is a use case and it will be open. If you send a request for a user name, You will be provided one, and then you can go and use it and see yourself about your data set.
Great. Thanks.
Thanks. Yep.
Next up, we have Jiang Sun from George Mason talking to us about what's new with Geoweaver. All right. And I'll say with this project, it's been, this Geoweaver had this initial boost of funding from ESIP. Since that funding, I think we've applied to at least, Geoweaver has been written into 2, possibly 3 additional proposals. It was awarded, it won a challenge through NGA, and it has continued to be developed, most importantly because it solves a really critical challenge for a machine learning expert like Xiang. So let's hear a little bit more about Geoweaver.
Thank you, Annie. So this Geoweaver project is funded by ESIP 1 year ago. In the past year, we have prototyped this system, and right now it's intensively used in our lab. So I want to update with latest progress here. So the original motive of developing this system is because we are working on machine learning experiment, and we have a lot of troubles to make our AI models work. So we seek for reasons, and we found that there are too many things, just a lot of compatibility issues, and with the platform, servers, operating systems, libraries, software, and a lot of unpredicted issues with the versions of those things. And we also involved multiple programming languages in our workflow, because AI model is most of the time is spent on pre-processing data. So in that pre-processing, we used a lot of programming language like R, Python, C++, Java, and all these things. We do not have one single tool to manage them. So we overlooked all the existing workflow systems and found none of them can solve this problem. So we want to develop a new workflow management tool to address that specifically for AI workflow, but it can work for other workflows as well. So what is Geoweaver? Geoweaver generally is a web-based scientific workflow management system. So it has integrated all the essential capabilities of composing, executing, managing, and disseminating AI workflows. That workflow can be executed on multiple platforms at the same time. You can link the processes on Amazon Web Services and the Google Cloud and all your local servers or your own laptop machines. Link all those processes into one single workflow and save it and disseminate or reproducing that workflow. Geoweaver can do that, and it's right now an open source project on the GitHub and license at MIT. So anybody can reuse that with modification. So this is a link. It's under that ECIP Fed repository, ECIP Fed umbrella account. So this is the interface, and don't misunderstand those windows are my laptop windows. It's Geoweaver Windows. It's just the style is Mac style. So you will, when you are using Geoweaver, it's like you are using your own laptop. So it will feel like it's pretty compatible with your user habit you have formed on your laptop. So it has three groups: the host, process, and workflows. The host is like distributed platforms, servers, Amazon instances, or Google Cloud instances. The process is a script, like a shell script, Python, Jupyter Notebook, or some built-in processes. And the workflow is a link, a flow graph of multiple processes linked together. And I think I need to mention why exactly we built Geoweaver, because we want to turn the large-scale AI pipelines into manageable workflows, and we want to boost the utilization of the existing cyber infrastructure, because since the Google, the Amazon, they have all those services provided, we kind of discarding or wasting our existing servers. They are running without running anything on them. So we want to integrate the public and the private resources together to do that AI workflow, to make sure that every resource is fully utilized. And we also want to enhancing the efficiency of AI model life cycles, and enable the tracking of provenance by recording the execution logs of every workflow run in structured tables. So you don't have to worry about the provenance. Geoweaver will record every execution of the process for you. You can query them at any time in the future to understand why the script worked one time, but right now it doesn't work. So what's the reason within that? And the fifth reason is we want to prove that we want to use large-scale distributed deep learning models to classify some like set images. Actually, we have already used the Geoweaver in multiple deep learning researches in our center, and that is conducted by some scientists in our center already. So I will introduce that later. So how does Geoweaver work? So right now it can be installed on Windows, Linux, and Mac. So it's like it's compatible with all the mainstream operating systems. And the installation is very simple. The first step is clone this GitHub repository using this command in your terminal. I think if you are using the Mac, that will be very simple. The second step is go to this folder and give this installation script the permission to run, and then execute it, and that's it. So after this script is finished, Geoweaver will be up and running. So you can visit the interface by entering this link in your browser. So this is some demo of how to use Geoweaver to run your Python-based deep learning experiment. So first, I opened a window. This window links all the files of that server. So I can browse all the folders in this window. Then I open this window to check, to edit my existing deep learning program in Python. So I come out this line and saved it, and click this button to run the code on the server, and I just choose the server and the Python environment and input the password of the server. So every run you have to input the server password unless you check that box, say do not ask a password again. But Geoweaver does not store your password on the server side. All your information is kept on your local machine, so you don't worry about so all the passwords are encrypted in the web communication. So we make sure that the privacy is protected. And after the workflow is executed, then you can see I can click on the file window to download that result at any time. So it's pretty useful for people, running their experiment on the remote servers. And the other benefits of Geoweaver is like it can automate the pre-processing, post-processing of deep learning, enable the large dataset processing for small groups because we understand that a lot of AI research groups are small groups. It's like one or two people working on AI. It's not like a Google group or Amazon. They have hundreds of people working on the same task. In the academia, only one or two people in one group. So we understand that situation, and we provide as much visibility as possible to them to organize their workflows. And we also want to help them to enhance their reproducibility of their experiment. So anybody want to rerun that workflow, it will be there. It will be there for you to check. And our unique features, which make Geoweaver a very unique solution in the existing market of workflow management system, is we have these 5 features. It can compose hybrid workflow, and it allows you to fully access the files, and it allows the hidden data flow, and it separates the code from the real machine. So you don't have to worry about once the server is collapsed and the disk is destroyed, your code, your workflow is still there. So that's another feature of Geoweaver. And it also records the process-oriented provenance, so which is much better than the data-oriented provenance to store for a long time. So recent progress is we are working on integrating the Jupyter Notebook, because now we only can execute the Jupyter Notebook and we cannot edit the notebook in the Geoweaver. So we want to integrate the editing notebook capability in Geoweaver maybe this next month. And if once that thing is done, then we will be able to use Pangeo in Geoweaver as well. And we will also want to develop their workflow process stop, resume, cancel function. And we will add a user management module later. So some scientists in our center are using Geoweaver to communicate with our servers every day. So this is one case. This is a task to recognize the central pivot irrigation system from the remote sensing data. The deep learning model used is, I think it's a ULET and the FCN32. And this is another study another scientist in our center is working on. They work on predicting the yield of soybean, and the result is pretty good. He did this research through Geoweaver on the Geobrain cloud, which is our private cloud in GMU, and the result is quite similar with the USDA predicted value. And they will also use the Geoweaver on helping processing their monitoring products of agriculture drought for the globe. And this data is like every update. This data is updated every 2 weeks, and every data is 2 gigabytes. So we have already done this for the past 20 years, and the whole data is like 20, 30 terabytes. And the Geoweaver help us to organize all these processing workflows, and we run it every 2 weeks, and it works fine. And this is a very interesting research have used the Geoweaver to do their training and recognizing diatoms. It's one of the algae in the coastal state, I think. So there is, I think, a very few scientists in the world can recognize these things. Even they are expert, they cannot tell all the names of the diatoms. There is thousands of diatoms in the world, and maybe tens of maybe hundreds of diatoms are discovered every year. And the scientists in all over the world, for example, in Germany, they will discover a diatom and name it after the scientist's name. And maybe the scientists in US discover that again and named after his name, and that will have a very serious confusion in the taxonomy. So we use deep learning to recognize these diatoms to actually accurately to distinguish that feature of each diatom and correctly, to save them, to save the scientists, because scientists spend way much time on labeling these things. They have a lot of labels. We use that label to train our data model. This work is also done through the, through the Geoweaver. So our future work is, future work for the next year, for 2020, is we will integrate the Google Earth Engine and the Google Colab for the skilled deep learning training. And we're also trying to integrate the Amazon machine learning services. And we also will integrate open source solutions like Spark and Hadoop for machine learning. We also want to integrate with the existing supercomputers, which is built as clusters in next year. And we have received a lot of resources and support from, of course, this is funded, incubated by the Exceed Lab, and we also used a lot of code from the NSF SCube Cyber Collector. And we have received a lot of consulting services from SGI, and they provided us with marketing consulting and development consulting. So we really appreciate that. We also received the support from AGU for us to promote our product. Thank you. That's it. Any questions?
All right. I love hearing Geoweaver talks and seeing how this project continues to evolve, mostly because it is solving a real challenge for this very prestigious AI group at George Mason, and we hope that it continues to be developed and get awarded more funding, because we think it could solve problems for a lot of other folks. So, Ag, do you want to come up next?
Good afternoon, everyone, or good morning, rather. My name is Agli Amico, and today I'm going to talk about the 3D printed weather stations for education, citizen science, and research. I was here, I guess, last summer for the ESIP conference, and we received a small grant funding, and today I'm going to be giving an update on the on our progress with the 3D printed weather stations. So we're looking at this from the perspective of Internet of Things, where it's an open weather station that's for everyone and allowed to be deployed anywhere. That's sort of the overall goal. The IoTWX is inspired by the 3D Pause, which is a 3D printed automated weather station that INCAR had developed, and it's a really advanced weather system, but it's a weather system that is actually really difficult to put together, and that it has all the connected systems, and it was really difficult to deploy in the field. So this project it borrows from that concept and sort of builds on it from a new perspective of Internet of Things, or of a more portable, modularized sort of system. So basically, the idea of this is to help support rapid development and deployment, and we use Grove-based connectors and and sensors that allow us to connect to the weather station a lot easier. We're looking to encourage broad educational engagement and software pedagogy. We build upon sort of MicroPython and CircuitPython for microcontrollers. So that's essentially how we're trying to make this process a bit easier for deployment. So why IoT-WX? The ESIP grant supported sort of some core accomplishments so far, even though we still have a little ways to go. We're looking at, one is reducing the learning curve to eliminate soldering and a lot of the wiring. So the initial design had a lot of wiring and customized soldering and all of that. So we're eliminating those issues from the process. Flexible sort of communications mechanisms and data storage options is another thing we're working on, working with cords, working with being able to do communications across different platforms. Next is fewer 3D printed parts and more integrated sort of PVC pipes. As you can see in this example here, we're just kind of using some PVC pipe to make the stand, and we're reducing the number of 3D printed, and we're reducing the number of 3D printed parts. So you can put that up here. Thank you. So also you'll see that there's, what we also will do is have fewer wiring to make the wires, because we're using Grove connected wires, that allows for the systems to all be connected without a lot of custom custom soldering and wiring and all of that. Lastly, we want to decrease the footprint of the weather station in general, so that the system doesn't, take up too much space, and also have the ability to flash all the software and put all the information onto the microcontrollers easily through a GitHub repository, and that will simplify updates and make maintaining the system easier. So these are all sort of the platforms that we're trying to put in place now to make the system more user-friendly for rapid deployment and for educational purposes. So one of the things we're doing is we're trying to reimagine, as I was mentioning before, the weather station in a sort of Internet of Things sort of approach, and that is to modularize the system. In other words, have different nodes. So you might have, in this case, we have an air node, which measures a radiation shield, which measures air temperature, humidity, VOC, so or kind of like pollution. Then we also have another wind node. Wind node here, what we've done is we've combined the anemometer and the wind vane, and we've used digital sensors instead of the other Hall effect type of sensors. And what that allows us to do is it allows us to reduce the amount of time that will be used on calibration and just make life a lot easier, since they're all sort of digital sensors that can be used within in this system. So with these separate nodes, we also have another compute node, which allows us to use things like perhaps a Raspberry Pi, or even a more advanced edge computing sort of systems. So these nodes can, basically they can perform very simple measurements. For example, an air node would essentially just measure, record the temperature, pressure, relative humidity, or it can do more advanced activities. You could have a camera, for example, on a node, and that camera could look at clouds or look at surface conditions, run AI to actually help do decision support things in the field. So each node can have a sort of a flexible purpose depending on the way you would like to use the system in the field. Next, the architectures can support different protocols: Wi-Fi, LoRa, MQTT, all kinds of different communications protocols. And that's what we're trying to do, is to make this flexible, because depending on where you want to deploy the system, communications will be a very important issue. So if you look at the wind node here, this arrow node, this is one thing that we've done differently. Previously, these were two separate units. And of course, when you have two separate units, you're going to have power and all of the components associated with them. So what we've done is we've combined them into one system, and we're testing it with a thing called a slip ring, which basically allows it to spin around or turn, or in this case to spin, but without the wires inside the sensors getting tied up. So basically it allows the accelerometer here to spin, and in this case we have a digital compass that it will as this thing moves, it just shows where the direction is, and in that case it allows us to not have to do detailed calibration from, say, a Hall effect sensor that was basically looking at using a magnet to measure the amounts of ticks. So this is just a sort of a different approach that allows us to make the system a bit more complex, compact. So that's one of the things that we've been doing, and as you can see here on some of the designs here, we've been going through various different design options, and we even have a potential future option where we may even be combining the radiation shield all into one system, where the radiation shield, as you can see, would fit sort of within the middle section here. So that's another sort of compacting of the design. By compacting the design like that, that actually allows for less 3D printed parts and a less amount of time and money to print 3D printed items, because it does take time or money or both to print these things. So now, sort of giving sort of a general base background on where we are with the various different nodes. This is sort of a progress report so far. What you'll see is that on the arrow node, that one is fairly far along in that we've got the design bit done in terms of what we're going to do with the wiring and the hubs inside of the platform, and we're also now testing the arrow node with the new microcontrollers inside of the radiation shield, and we're working on deployments, which I will be discussing as well in just a second here. The hydro node is, we've got the design complete. It's a new rain bucket design, which will be testing that and doing a deployment in the early spring. The Atmos node, which is the radiation shield, you'll see we've got that design ready, and we're testing the radiation shield. And essentially during these tests, one of the things we're really concerned on is really making sure the communications, and we're able to get the data into cords in a reliable manner. So that's sort of the last bit here, is hooking this up to power. And since we're using, unlike the previous version, we're using a microcontroller, obviously it's going to use a lot less power. And that's one of the things that we'd like to do, because when we were out in Hawaii, we did a deployment prior to this in Hawaii. And of course, we were using the old design, so you had Raspberry Pis, and those things are kind of power hogs. So instead of using that, what we're doing is using smaller LiPo-based sort of batteries and solar panels that allow us to power the system, and then of course use a sort of protocol, communications protocol called MQTT that allows us to take the data from the sensors and put it through the internet onto cores. So one of the things we're doing now is we're kind of field testing and sort of testing out the different print designs in real time, and figuring out, okay, how portable is this thing? Can we, you know, can we do some field tests to make sure that we can get the wind arrow node working properly, especially with the slip ring concept. So the slip ring concept allows for both of these things to work inside of one unit and the wires to not get tied up. So we've got that, and we're testing those things for deployment. We're going to do a 2-week sort of burn-in test, and we've got those items printing now as we speak. We're printing out the full stations, because we're going to, part of the ESIP grant was to have a small mesonet of 3 or 4 stations that we'll be deploying, and then you can actually monitor all 4 of these different stations at once to sort of see local effects. We're looking at other things like different leveling mechanisms and sort of new sort of harnesses. That's what we're also putting down to hold some of the sensors in place, so that the sensors can stay secure inside of the system. So, and lastly, we're also looking at, you know, hardening the communications protocols, because that are some of the issues where you get things working, and because of, you know, particulars of the microcontrollers and the MicroPython and the way these microcontrollers only have so much memory, sometimes communications becomes an issue with getting that data to work. So that's those are some of the field tests that we're trying to work on now in the next few weeks to get this thing going. And the reason why we want to do that is because we would like our deployment is going to be in Puerto Rico. We worked with Keith Mall, one of the partners on this. He's in Boulder right now. He's not here. He's also an ESIP member. But basically, one of our students that we worked with at INCARV in the SOARS program, she's at the University of Puerto Rico. And as you know, Puerto Rico has had sort of a, you know, not great time in terms of earthquakes and hurricanes and whatnot. So the network of the weather stations in Puerto Rico, as you can see, is, you know, you have a bunch of stations on the West Coast, and, you know, radar. You have a few other small, you know, other privately run weather stations along the southern coast there, but you don't really have a huge network of weather stations. And one of her projects, her graduate study was on doing mesoscale modeling using, you know, of Puerto Rico. And, you know, obviously there's a huge amount of topography here. There's mountains all along the middle, and the gaps in the mesonets isn't very helpful for understanding sort of mesoscale effects, especially when it comes to hurricanes and other storms that come through there. So what our goal is to do after we've completed the test of the stations is to get them to Puerto Rico, and allow them to, the local students there to basically, and work with the local National Weather Service office to deploy these stations in Puerto Rico. And of course, if a hurricane comes and these things are modular, you know, you can easily replace the parts and the stations. And that's one of the things that they would like, something that's quick and relatively easy to deploy. And right now we're looking at a tentative date of early this spring to put this out there. And, you know, basically right now we're printing and testing basically is in progress. They will also print and test at least a couple of additional stations while they're, you know, the students are out there. And then we'll be doing a deployment. And this was all part of the ESIP sort of budget we were looking at and proposal, because part of that proposal was, you know, not only are we going to have sort of a station, but we want to actually deploy it in a 3 or 4 station, sort of a local mesonet. And this Puerto Rico example, given the amount of gaps that they have in their mesonet and the sort of the local contacts that we have on the ground, is a really good example and a really good sort of contained case study. So if you look at this island, it's about 100 miles across from east to west. So it's a relatively contained place. So this is another example that we could that we're looking at doing a field deployment with. And lastly, we would like to collaborate. We still have a ways to go in terms of, you know, completing and finishing the testing and working on various different aspects. We are currently redesigning the station footprint and some of the sort of key components of the station, especially with respect to the electronics. We have several small grants to sort of build and deploy these stations in 2020. So part of the goal of this year is to get to deployment and is to burn these stations in and get them out there in the field and deployed with a smaller footprint. And we're testing, and you'll see later on tonight, this afternoon, we're testing with teachers various different modules. So what we'd like to do is have like an instruction module or something where you can actually, I'll take this thing apart, and then the teachers will this afternoon put it back together and just figure out, okay, what is the process of actually putting these things together? Is that straightforward? And because it's a modular system, and I'm a teacher, I might not put a whole weather station together at once, like, you know, all of these different nodes. I could just have one classroom session on one node. And that node would be, hey, just the radiation shield. We put together a radiation shield, and that could be one class. You turn it on, you look at the data that's coming from it. Then there may be other modules, for example, that talk about, you know, the NGSS, which is the sort of science standards for educators. You can start picking off different aspects of the NGSS standards to have in various different modules. So yeah, so we have definitely certainly have interest from different potential partners, universities and schools, and we're actively seeking grant funding and partnerships to sort of see where this goes. And we appreciate and certainly excited about the support and collaborations we've had here with ESIP, because, you know, of course, this is sort of the fusion of sort of looking at data and field work, and of course being able to integrate that with the instrumentation. So I think this is a really exciting project, and I look forward to working with ESIP and everyone here in the future.
So just an estimate of relative cost of a weather station. So once this is operational, there we go. What's your ballpark figure?
So our ballpark figure is what we want to do is we want to break a whole weather station, maybe about 300 to 400-ish. But then we'd break it down because you can purchase it per node. And this includes, you know, you have to have the PVC pipe and all of that. So a radiation shield node may be $40 to $60. Wind node, and this includes printing, whether or not you purchase or print yourself. A weather air node may be another $50, and then a rain bucket. So each node you can purchase separately, or you can try to build the station as a whole system. So one of the things we're also trying to do, and that's one of the reasons why we may be combining certain things, is we're trying to bring that cost down, but it's still significantly lower than the $1,100 or so of the original craziness that we had before.
And you're sort of related to that, how long does it take to print one?
Yeah, the print time, I don't have the exact number of the new ones, so we've reduced the current print time. The previous print time was, I believe it was almost 200 hours, and we've reduced that down to like 20 hours of printing. I mean, it's reduced down by like 70, almost 80% in terms of just the sheer amount of time to print.
And then to put it together, I guess we'll find out this afternoon how long it
Yeah,
takes to put it together.
We'll find out this afternoon in
Shorter
terms of
than
just
a day?
like the physical pieces of putting together like one node. We're trying to make one node equal to one classroom session. So we'd like one node, for example, the radiation shield to be, 40-minute sort of situation to put together. And that, now, of course, if you're putting it together and you already know what a radiation shield looks like inside and out, that's one thing versus someone who's never seen one before, that takes a different,
Is the radiation shield one piece or is it?
It's multiple pieces. So this one, it has like each one of those each one of those layers, shields are different pieces that snap together.
Oh, okay.
And then there are like these rings that come around them that you have to also snap in. And then of course you have to then put the electronics in there. So there's different pieces, but it's just a matter of trying to see how efficient you can put them together. And it also depends on your familiarity with it. So we're just trying to make manuals and things to just explain it as easily as possible.
Great. Okay, thanks.
It's very cool. All right, Amanda, do you want to come up? Actually, can I also do a live demo? Can I do a live demo? Okay.
Hi, I'm Amanda Tan, and I have been working on setting up scalable serverless workflows for processing CubeSat imagery to identify flowering hotspots in subalpine meadows. It's a very long title for basically trying to say that I've been setting up, trying to figure out how to get flowering hotspots from planet data using serverless computing. So my collaborator at the University of Washington is a PhD student, very motivated. His name is Aji John. And the problem that we're trying to address with building the scalable serverless workflow is really trying to identify phenology shifts. So we're trying to look at understanding how peak flowering has changed in Mount Rainier. This image here shows the sites where we have both citizen science data and also observation data of the timing of flowering. And there's two objectives. One is that we wanted to use serverless computing. So specifically on Amazon Web Services, it's called Lambda, where all you have to do is write code and automate that execution of the code through this Lambda service on Amazon Web Services. And then also to understand if planet imagery can sufficiently predict flowering times. And one of the reasons why we're using serverless computing as opposed to just writing your code, writing all your code and then just running it on, let's say, an Amazon instance or running it on your laptop, is because we wanted to lower the barrier to entry of being able to utilize some of the cloud processing power. The Lambda service on AWS actually allows you to run up to, I think, a few, like 10,000 simultaneous code execution at any one time. And so if you think about that, that means that we're able to harness the scalability of the cloud as opposed to running a one long workflow and waiting for hours and hours for it to process. And also the other thing again is with current satellite and not the small high resolution data sets, we have been unable to actually look at peak flowering times because you need very minute scale satellite imagery. And we've been collaborating with another ESIP funded project, which was funded, I think, maybe last year, on inferring snow cover from planet imagery. So we're trying to mesh building these serverless workflows with both getting the snow cover data and also the NDVI. So what is an example of a serverless workflow? In this use case, we want to query planet imagery, planet data to detect seasonal changes to get NDVI. So just a very simple workflow. This is what it looks like. You start searching for the data that you need, and you clip the data to your area of interest. You search for it, you activate it, you clip it, and then you get the NDVI, and then you aggregate it, and then that's the end of it. But how do you actually write code to do this on serverless computing and not on just executing an entire bunch of code at one time? So I'm going to actually pull up and hopefully pull this up. So we've actually uploaded an example of a notebook of these codes. So each box of these code is actually one Lambda function. So a Lambda function actually executes this code and then it moves on to the next step. So with the serverless workflow, it executes this boxes of code in a continuous mode. Is there another word for continuous? But it executes it continuously so that once something finishes, then you execute another function. And here, all these little boxes that you see is each code that we've written as a Lambda function. So if you go into our AWS account and you click on Lambda, you'll see that there's multiple functions, about 10 or 13 of them, and all of them contain Python code that looks something like this. So we import a bunch of packages. We load the environment variables, which contains a planet API key so that we can actually get the data. And then we define a geometry of the area that we're interested in. So we're actually clipping all this planet data to the coordinates that we specified here. And again, each block of code is a function in Lambda. And I'm going to scroll down a little bit more. And then it'll return some kind of data. So for example, here it'll return all these little buckets of available planet data that's been clipped to our area of interest, and they'll store it in a temporary Lambda drive somewhere on the cloud. And then when it moves on to the next function, it will know how to refer back to the data that's stored on this temporary folder on the cloud. And right here, we're getting the metadata, so the results metadata right here, and it's dumping back a whole bunch of results. And so there's a lot of results. And then we are loading each of this. So the results there are each of them a URL or a link to where we can actually download the actual planet data. And then, so for example, right here, we have an item ID that's been clipped to the area of interest that we want to get the data set for. And we run this function here that actually really just gets you, activates this, this URL. So with planet data, you kind of have to activate that URL that you get so that Planet actually will start the process of downloading data and storing it somewhere for you to access it later. And then after we actually search and activate the data, we are able to then do things like extract the actual data that's contained in these little planet files. And the thing that we're really interested in looking at is, for example, getting the NDVI. And here, basically, again, each of these boxes are actually functions that we run in AWS Lambda. And once we start that workflow, it just continuously runs through a whole gamut of Lambda functions, and it spits this image back at us which is really, if you run, for example, this code right here, this entire block of code in a Jupyter notebook, this is what you would get. This is an example of the data set that you would get. But if you're running your code on serverless, you will not be seeing this image. So the way that we actually run the serverless workflow is by command line. So you log on to your terminal, or you log on to a Linux shell, and we're working towards being able to just say, serverless, run this workflow, which has a whole bunch of Lambda functions already specified in it. So it's basically a configuration file. So you would say serverless, run this configuration file, and it'll go into your AWS account, and then it would run all these Lambda functions. And then you can do things like, once you have that data, the NDVI data set, you can do things like plot an NDVI histogram. And this really, the idea behind this really is to take away the need for you to maybe even run your own AWS account or your own Lambda function on your AWS account. What we are working towards is this one-line command of being able to say, serverless configuration file. And that's all it does. And that's all you need to type in. That's all a researcher needs to type in order to actually get processes to run on the cloud. And so that's the first part, and we've been spending a lot of time in actually getting that bit going. We're trying to test different thresholds of how much code you can actually put into your Lambda functions. So if you're, I don't know, if you're familiar with Lambda, AWS Lambda, the execution time for each block of code can only be 5 minutes. So if you're writing code that is, thousands and thousands of lines long, that won't work on AWS. So we're trying to find that threshold of what really is the most efficient way of utilizing AWS Lambda. And then once we've gotten this, all these NDVI, the next step that we wanted to do was really to calculate and look at trying to see if we can use planet data to detect the flowering. And so some of the initial results that we've gotten is, so on the right-hand side, you'll see that that's in situ monitoring. So that is from a lab that's actually set up in Mount Rainier to look at flowering phenology. And then the other is using citizen science data, which is reported by people actually visiting Mount Rainier and downloading an app and actually reporting the flowering times. And the results that we got was that if we just use planet data at 3-meter resolution, high resolution data, it actually doesn't work very well. And how we actually get that is by using random forest deep learning on the planet data. And the next thing that we did was try to figure out if the 3-meter high resolution data doesn't work, is there some other way? Can we get more data into our machine learning algorithm? Can we use even more data sets? So we tried using coupling the planet data with Landsat data and also with Sentinel data. And we see that for the most part in 2014, it was like, whatever. But for 2013 and 2015, it's actually closer if we couple planet data with Landsat data, that we actually kind of get a result, a predicted flowering result that's closer to the observed data. And on the y-axis really is looking at what day the peak flowering is occurring. And you can see that actually just based on the observed results, that peak flowering from 2013 to 2015 is actually moving further and further up the year. So it's happening earlier and earlier. And that's something that we want to capture with this combination of using planet imagery and Landsat and Sentinel. Some of the reasons why we're actually trying to use satellite data to get at this peak flowering phenology is because oftentimes all these in situ monitoring or even citizen science data sets, they're not sustainable. It's contingent on actually having somebody go up there and monitor those stations, or it's really self-reported and it's not really accurate. So we're trying to figure out ways to actually make this observation or this predictions more sustainable. And I think I am at the end of my talk. Great, thank you.
Innovation efforts broadly in the CSIP, come to the front of the room. We're going to wrap up by having kind of a discussion. If you don't feel like it, please stay in your chair. It'll be a little bit easier as everyone comes kind of towards the front. You're good. I would say I'll even say first, yeah, 1, 2, 3, first 5 rows. And you don't have to just go. So probably burn through the, the time frame. Oh yeah.
Okay. We've heard through kind of when the lab is presented in the larger sessions that currently our model of innovation within ESIP is to give you guys that have been funded or others that are interested this small pot of money and be fairly hands-off and just say you had a really good idea, go about and do the work and come back and report to our community. And then we hope to keep in touch with you and say who else should know about your project. And our dollar limits are between, some people submit for $4,000 because it's just equipment. Other people go and really maximize the budget out to $10,000. So I'd like to use this time to hear back either from our PIs or others in the room if you have any feedback on this model, or if there are things that rather than more money would be a bigger lift, like the thing that would help you get your project to the next stage. And for those that aren't our funded PIs, what motivates you or within your organizations or agencies, how could ESIP through our innovation kind of program help support you? So does anyone, particularly our PIs, have any initial feedback just on how we do innovation within ESIP and feedback on that? Ag?
I think if we form like a technical network that they can participate and help each other, this will be very helpful for example, a Java developer or admin for the systems, or this can participate in like a small part of his time and will reduce the learning curve of the project constructor. I think this may be initiatives that can be done with the labs to form like a technician networks, and this is
great. Thank you. Any else, Jensen?
Oops. Yeah, so I think this lab is amazing. For the improvement part, I think we should find more places for either ESIP lab projects to collaborate together. There is a lot of areas that because for the project it's a prototype, because we cannot do anything too complicated. But for the first step, we need to find users. Actually, the first best users is actually other ESIP project lab participants. So like Geoweaver and the weather station, they can collect together, or Geoweaver and Serverless, Lambda, they can collect together and be users to each other to first prototype the demo case and to attract more users from the participants from outside. That's my think.
All right, anyone else? Amanda or?
Go really quickly. So for me, obviously more, you mentioned rather than more money, but more money is always good. Mostly because I think like for sustainability and from a sustainability standpoint, 6 months is really fast. You conceive the project and by the time you're, you've gotten past the learning curve, then time's up. So that would be if there was a possibility of actually getting a bit more funds. The other thing is, I wonder if it would make sense to have, other than outside of the ESIP meetings, where sometimes some of the PIs or some of the participants of the ESIP lab cannot attend, to have showcase of their projects, so like workshops, or maybe even webinars of, this is this amazing project that we've done through the ESIP lab. Come and listen to it and come and participate.
Great. Yeah, so one idea, so on the first point on the funding, I have been thinking about, and so for those that don't know, this is Ben Robert Spiro. He's our lab fellow, and he's going to be helping with the RFP process. The next RFP closes on Friday. But we've also been thinking about maybe intentional calls for projects that have already been funded to have, you can only, it's a special RFP that if you've been funded within the lab and you need one more additional step, and we don't want to keep like stringing projects into 1,000 and 10,000 bit pieces of funding, but because again, we're in that prototype stage, that one idea was either having a call for less than $10,000, but some development money, but also more importantly, what we've heard back is that that maybe an additional without applying to the RFP process, but there is a means to get money for tutorial building or documentation. So saying, don't worry about that during your initial prototype stage. Kick the tires of the technology, work through that part. But then if you think you're going to move forward, there's an additional $2,000 available, some more credits to actually develop the documentation or just whatever you would need to bring people in, because good documentation just takes a long time. I mean, we participate in Google Summer of Code, and they just started a Google Summer of Docs program because I think of that issue, that we want to spend the time on the technology development, but we all acknowledge the tutorial and documentation side of things are critical. So, so I think that's one specific additional call that we've thought of. And certainly if you're using cloud services, everyone wants tutorials on like, well, how did you do that with a specific use case example? The other part, it sounded like just the meetups, and Abdullah, this goes to your point as well, in terms of the network. That we need to do a better job of maybe at other professional meetings coming together and being somehow identified as an ESIP lab project. So I don't know if that means like at AGU, or if you're going to a meeting that we have meetups, or using some of our funding to have technology forums where we're inviting previously funded lab projects to come together. And maybe that would be a place that we could all be networking and wanting to learn about each other's projects. So does that, kind of get any other feedback just on the kind of how yeah, go ahead. And what's your name? You can say name and where you're from.
Hi, my name's Jonathan Blythe. I work for the government in the Bureau of Ocean Energy Management. So I was just interested because we fund a lot of research in ocean science. And so this is more kind of interest to what I do on a day-to-day basis. The one thing I'd like to draw out from a lot of the, at least two of the projects, the weather station project, there's a demonstration going on in Puerto Rico, and then the other one with satellite data and Mount Rainier. And I think one opportunity you have is at a meeting like this, especially like the summer meeting in Vermont, if you co-locate a demonstration with a local community and have people come in and show that how that that really had a local impact, I think that would generate a lot more interest, both bringing people in from the community, so you have a real case study and you can evaluate that more deeply. And it might be a good way to bring people together also from the community that around a common problem. So rather than having one project in Vermont, maybe see if people can bring different projects together into one larger demonstration. Just an idea.
Yeah, Shana.
Do you use technology mentors? Like, so within the ESIP community, there are many people who would have expertise in cloud computing or data visualization or some of the different areas that maybe the labs are funding, and maybe it would be helpful to introduce members to some of the ESIP lab recipients.
Yeah, and that's, I mean, that's part of the sticky wicket, because we want to provide lab projects a forum to say what they're doing, and even in the application process to say, like, we have all of these experts, and we've been successful with that sometime when a project has presented and then the right people are in the room and can go talk to them, but that mentoring part of things is something that I've struggled with. At what point do you, at what point do you bring in that additional expert, or do you just put it out there to say, hey, if you have a question, we've got a community of experts here, please lean on our resources, get on the, we have a collaboration structure of like the clusters, like get on that call, post to our GitHub repo where we have, or not GitHub, but Slack, where there's 700 of these people that are on our general channel. So maybe just, again, letting the PIs do that initial involvement, but do a better job of letting everyone know that we do have a network of experts on ESIP-all, on Slack, in our collaboration areas. Yeah.
And the flip side, of course, is letting those people who might act in that mentor role know that there may be people doing these projects who might be looking for their expertise.
Yeah. I mean, I know with USGS CDI, what time is it? I don't want to hold that anyone. 2 minutes. Okay. Sure, Karen, go ahead.
Oh, okay. Karen Moe, and retired NASA. What I wondered is if I'm thinking of a couple of schools that might be interested in my neighborhood, say in the weather station. And I'm also thinking about, I joined our Maryland Plant Society. They might be interested in, something like, the tools that you're developing, hotspot detectors. If there was, say, a short video of your project that, when I'm talking to people, I could say, I learned about this project, and you might be interested in kind of learning more about it and getting involved.
Yeah, the short videos actually, and I'll have this in my last comment, but I would say that, certainly our PIs and other people in the room, that this is something that we want to work for everyone. So if you do have comments, to keep them coming. I was just at a National Geographic the other day and talking with them about a couple of things. And part of their grants program is they have to submit, anyone applying to their Explorer grants, which are ESIP size, they're up $10,000 or less. They have to submit a video talking about their project. And so another way would be at the end, submitting a video. In videos, I mean, people, some of them, there's now tools that can give a little bit more production value, but finding ways to make it easier to share something about your project, rather than maybe a recording at a meeting, but a 1-minute video of saying, this is what my project was about, and just a more maybe tangible or digestible form of communication about what you're working on, even if it's 30 seconds or less. Say, this is what I'm working on, and it's easier, it's more easy to share. So it's lunchtime. I want to thank everyone and thank our PIs. I love that we had such a diversity, starting with like metadata, machine learning and workflows, 3D printed weather stations, AWS, cloud stuff. I mean, I think it's great to show that breadth. So, so yeah, thanks everyone. Have a good lunch.